Hi, this is a recording of me using COMSOL Multiphysics to simulate a simple little problem where we'll study some blood flow through a capillary blood vessel network. So if you followed the instructions to install both the College of Engineering VPN and COMSOL Multiphysics, then you should be ready to run COMSOL. Remember, the first step is to run and connect to the college's VPN client. That's the Cisco AnyConnect Secure Mobile Client app here. I'll hit connect and log in with my my College of Engineering credentials. Remember, that's not your usual net ID login. It's the College of Engineering login. When I do that, I'll see this little padlock appear up here, meaning that I'm now connected. That means I am ready to run COMSOL Multiphysics, which is going to be living in here. It'll take a moment to start. All right, there we go. All right, so remember, the first step in all of these is to start with the model wizard here. I'm going to choose a 2D simulation first because, as we discussed in lecture, the 3D can take a lot more time to work, and so I'd rather get it working in 2D first. Now, for modeling fluid flow in a blood vessel, I'm going to choose the laminar flow physics. It appears here under recently used, but it also lives under fluid flow, single phase flow, laminar flow, in case you can't find it up here. So there's laminar flow. I'm going to click add to add that physics to my simulation. There it is. And then click here to go on to the study. And I'm going to use a stationary study here, not a time-dependent study, because again, it's easier to run these things in stationary first. And what we're going to play with here doesn't require solving at multiple time points. All right, I click done down there. And then I come up with the default COMSOL model like this. So the first thing I see here is under geometry or the length units. I always want to change that unit to something that's more convenient for what I'm trying to simulate. In the case of blood vessels, a scale on the order of millimeters makes sense to me. So now that's updated the scale of this to millimeters. And I also like to zoom out so I can see the full range over which I am going to draw my blood vessel network. How about like that? Okay, that's good. So I'm looking at a couple centimeters worth of square surface there. Great, so now I'm ready to start drawing my blood vessels. I like to build everything out of rectangles if I can, so right up here is draw a rectangle. So I'm going to start with a blood vessel that is 1 or 2 millimeters across going down to here. It's going to now branch into another rectangle here like that. It's about like that. I'm going to draw some more. These represent maybe the capillaries in your blood vessels. And then they're going to recombine after going through your lungs or your body or whatever's interesting. They'll combine again into another blood vessel, and they'll be on their way back to the heart or the lungs or whatever it is we're trying to simulate. So this just shows a very simple branching network of blood vessels. Okay, so there's rectangles of all of those that appeared over here, and you see COMSOL automatically puts this form union operator, meaning that all 6 of those rectangles are all going to be combined into one fluid path when I'm done, which is what I want. That's great. Okay, so I'm done with this. The next step, and remember my usual process is to go down this list over here. So once I'm done with one point here, I look down the list and see that materials catches my eye. So I'm ready to add in material. When I click on it, it says alert, domains 1 through 6 need a material assigned to them. So let's do that now. I will right click on materials, and I could create a blank material if I want, but for this demo, for simplicity, I'm just going to add a material from the library using water as a sample material. It's not the same as blood, but it's good enough for this approximation. Now in the other video that I'm going to upload where I use solid mechanics, I'll create a blank material from scratch in that one. So if you want to see that, check out that video. Okay, here we add a material from the library. This appears over here. I can look at my recent materials, or I can just find under liquids and gases, liquids, and water. Now I'm going to click add to component, and if all goes well, after a moment, there we go. That took a moment. Everything turns blue, and here under the selection operator over here, I see domains 1 through 6 have all appeared, meaning that COMSOL has recognized that all 6 of these little these little blood vessels are filled with water in our simulation. So that's great. Now I can close this tab over here. And I can zoom extents to make a little better view of it over there. Okay, so that's done. And you see that the material comes preset with all the materials that matter in the simulation, in particular the viscosity and the density of the material. If I scroll over here, you can see the details of those values. So that's all ready to go. All right, so moving down the list over here, I see my laminar flow physics that was added. All the domains 1 through 6 are already attached to this physics, so that's correct. And then I can see what defaults COMSOL has used. The fluid properties by default are inherited from the material properties, water, and so that's correct. Nothing to change there. The initial values of everything in my simulation is fluids at rest, right? I see these zeros here. That means that all these fluids over here in my blood vessels are not initially moving. So if I simulate it now, I expect to see no motion at all. And we're going to add motion to it in a minute. And then looking at the boundary conditions, I see that all of the walls of this system here are called, all of the boundaries of this system here are called walls, right? And we can see all those 8 or so, oh no, there's more, all 26 or so boundaries have been added as walls. So here over here I see that they are highlighted in blue, and that means that by default COMSOL has set those to be walls where fluid doesn't flow in or out. It's a brick wall for fluid flow. Okay, we've done enough now that we can actually try to run our simulation. So let's right click on study 1, click compute, and we'll see what happens. Now we haven't intentionally added any flow to this yet, so I don't expect this to be very interesting, and in fact the results aren't terribly interesting, but I like to compute early on like this just to confirm that the simulation is working, and indeed it is working. So we see everything is colored green. The color bar over here tells us that green corresponds to 0 meter per second of fluid flow, and so that's unsurprising. We aren't intentionally flowing fluid inside of our blood vessel network here, and so these simulation results confirm that. But so far so good. I know that everything I've done so far is correct. Now I'm ready to go back up here under laminar flow and start to add more to it to make it more interesting, more lifelike, more like the system that I'm trying to model. So I'm going to right click on laminar flow, and you can see everything we had to have to choose from. The inlet and the outlet are most interesting for this problem. So I'm going to choose inlet. It's going to add an inlet entry down here. And you see in terms of boundary selection, this is already active, meaning, but this list here is empty. This is telling me that I am ready to now click on the boundaries over here on my model that I want to serve as inlets. So let's have this serve as my inlet. And then down here under the details, I can specify what I want that inlet to be. What's the fluid flow velocity at that inlet? It's in meters per second, so if I put a number like 1 meter per second, that's probably a little unrealistically fast. So instead I'm going to say 0.001 meters per second, so a millimeter per second, a nice slow flow of blood going into our blood vessel network. And then I need to add an outlet, so I'll right click on laminar flow again and add outlet. And then I specify, again, this is ready for me to click, I specify which domain here will be the outlet. And there's not much to configure down there. That's all just fine. Okay, so if I right click on study 1 again and click compute, now I don't expect to see just a sea of green. Now I expect to see, colors, indicating that there is a range of fluid flows inside that. So looking at this closely, I can see that there's a region of high flow here in the middle of this channel here and low flow on the edges. That's what's expected under laminar flow. There's actually a parabolic shaped distribution of flow rates in this channel, where the highest flow occurs in the very middle of the channel and the lowest flow occurs at the very edges, there and there. Then when the flow splits, we see that because the flow is following 2 different directions here, the flow rate changes in each one of those, and that's shown by the cooler colors in here, the greens showing a middle moderate flow rate, and then when they recombine, we're back up to the high flow rate up here. So that's great. So the final thing I'll add to this is, in terms of a visualization, I'd love to see some streamlines. For these sorts of fluid flow problems, it's really nice to be able to visualize the flow that particles, blood particles or cells would follow through this. I can create that by going down to my results and this velocity plot here. If I right click and say add streamlines, then the first step, you see this selector here is activated, and so it's waiting for me to click on the interface where those streamlines, the boundaries where those streamlines should originate. So that would correspond to my inlet shown there. So there we go, that's selected. Now it's going to put 20 streamlines by default on that boundary, and it's going to trace those through the fluid. So let's click plot up here and see what that does. And now you can see, hopefully, as I zoom in, it's added these nice streamlines. Let's zoom in on this section here. And we could follow where, for example, if there were a cell flowing through this, a cell located here would follow that streamline in that direction, but a cell located here would follow that streamline. So this is giving us a nice insight into what goes where inside of our little blood vessel network. All right, let's make one more change. I want to add a blockage to one side of this to simulate perhaps a thrombosis, a clot that might appear in your capillaries and would affect the flow of blood around the rest of your body. So I'm going to go back up here to geometry. In this case, I'm going to add a little circular region here, and see how I add this. I'm going to add it, about like that. Okay, I'm adding it in a way so that I'm going to subtract that circular region out of the rectangular channel regions. Remember the way COMSOL works, you draw the material that you're simulating. So in this case, we're simulating the fluid flow, so I'm drawing rectangles that represent the fluid flow, and then to create a clot or an obstruction on one side, I'm going to subtract out this circular area here from the remainder of the rectangles. So to do that, to subtract out a material from the rest of my flow, I'll right-click on Geometry, select Booleans and Partitions, and then select Difference. This lets us subtract one region out from another. It's useful for making a void or a hollow part within the simulation. So I select Difference, and immediately our selector here is active, and it says select the objects to add and the object to subtract. We're doing this first, okay? So the ones I want to keep in my system are the fluid channels. So that's all of you guys here. I'm going to click on every rectangle that represents what I originally drew as the blood vessels. Then I'm going to click down here to objects to subtract, make this selector active, and then I'm going to click my circle there. Right, that's the domain I want to subtract or carve out of my fluid channel in here. So if I click Build All Objects now, you'll see what happens. There, perfect. You see how that subtracted that circular region out of my blood vessel. And so this sort of would represent a bit of plaque or a thrombosis developing inside of a blood vessel that's going to cause a reduction of fluid flow, of blood flow in that area. Okay, let's go back down to Study and right-click and say Compute and see what happens to our blood flow in that region. All right, very good. So now, looking at the different colors, you see a higher flow now, the yellows in the region that is still open to flow, and a lower blood flow here in the region where the obstruction has occurred. But you see that where this thins down, the flow rate increases in that area. And this actually has interesting clinical implications. If a blood vessel flowing through this particularly is activated by some sort of shear stress, which can induce clotting, for example, and increase thrombosis. A blood vessel flowing through this region here will be experiencing a higher shear stress and might cause other problems. That's another reason why obstructions and clots like this are dangerous for people in their blood flow. We can zoom in a little bit and appreciate how the flow lines now don't quite split 50-50 across this. Now the dividing line is about over to here, meaning most of the blood cells will go this way, but some of them will continue to go this way and will squeak past through here. If I wanted, I could make this obstruction here even bigger and see as this blood vessel over here gets narrower and narrower, what happens to the distribution of flows across these. Okay, so that's my entire simulation for COMSOL Multiphysics for applying it to a neat little blood flow problem. So in Design Challenge 3, you're going to do something like this if you wish. You could do fluid flow or use solid mechanics, but be sure to do something different. Apply COMSOL Multiphysics to a different bioengineering problem that interests you. Okay, thank you, bye.